Hi, I hope you have seen this infinite radical many times before, and I also posted it 3 equals this infinite radical. Where did it go? Yes, 3 equals this infinite radical, and this job is done by Srinivasa Ramanujan. Ramanujan sir got this really cool, but one thing is that he started with 3 and he ended up with this infinite radical. And a natural question comes to everybody's mind is that if we start with this infinite radical, will we finish at 3? Or if we consider a sequence root 1 plus root 1 and then root 1 plus 2 root 1, then 1 plus 2 root 1 plus 3 root 1, then will that sequence converge to 3? Now, at first I didn't have that question in mind. One of you, Thinula, said that how do you solve if you have been given the last line? And here the question starts and the idea starts. And I said that go backwards, but that is not sufficient. Going backwards will not prove that the sequence will converge to 3. Then he said that that goes to infinity. I said no, it doesn't. Then how to prove that going backwards will suffice? That is, I can go from this infinite radical to 3. So he asked me to prove it. I also asked him to prove that this goes to infinity. Here he wrote that this goes to infinity. So I asked him to prove that. Now, for proving this, I wrote this explanation. I'll share this with you. See, if uh, Ramanujan sir proved that 3 is equal to this infinite radical. This is clear to us. Now, according to Thinula, this radical, infinite radical goes to infinity. I'm going to prove that wrong. How? Let us see. Let us see how that works. So for increasing this confusion, I expressed 4 as this infinite radical. But is it right? So to just justify Thinula, what I did is I represented this infinite radical, or I gave this infinite radical 2 values, one 3 and another is 4. So which one of these is correct? To prove that, we need to prove that this infinite radical will converge. So I considered this sequence 1, as I mentioned earlier, 1 plus root 1 plus 2 root 1, root 1 plus 2 root 1 plus root 3 root 1, and so on. And the nth term of this sequence will be root 1 plus 2 root 1 plus dot 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 plus n root 1. So I named this nth term un. Un equals root 1 plus 2 root 1 plus and so on, as I discussed above. So I have to prove that this converges to 3, and that will prove my statement that going backwards we can reach to 3. We can observe that this sequence in equation 3, this sequence in 3 is monotonically increasing. We can justify that. It is very easy. See this. Firstly it is 1 and then 1 plus 2 root 1, and that must be greater than 1. You can easily prove that this is an increasing sequence and it is monotonically increasing. And from equation 1 you can easily see that 3 is a bound. It is an upper bound of this sequence un. Okay, 3 is an upper bound of this sequence un. So we proved that un is monotonically increasing and bounded, and we know that monotonically increasing bounded sequences converge. So we prove that un converges. Now we have to prove that the limit is 3. What will we do to prove that the limit is 3? We choose an arbitrary epsilon greater than 0, but arbitrary epsilon which is arbitrarily small, greater than 0 and less than 3. If we find n equals n epsilon such that un equals this un is greater than 3 minus epsilon, then we have proved that 3 is the limit. Okay, so let us find the n. Firstly, put 3 minus epsilon equals 3r. So we get that r equals 1 minus epsilon by 3 is between 0 and 1. And so we need to show that un is greater than 3r. See, here I put 3 minus epsilon equals 3r. So this must be greater than 3r. un must be greater than 3r. And what is 3r? I put the value of 3 here. 1 plus 2 root 1 plus 2 root 1 plus 3 root 1 plus 4 root 1, so on. This value of 3 I will put here. So we get this thing. And un, the value of un from here. So I am putting the value of un and I am putting the value 3 into r here. So now let us see how Ramanujan thought of this infinite radical. So after seeing this, I will proceed from here. See, we can observe that n plus 2 whole square is equal to n square plus 4n plus 4, and that is equal to n square plus 4n plus 3 plus 1, which is equal to 3n plus 1 into 3n plus which is equal to n plus 1 into n plus 3 plus 1. Now suppose fn equals n into n plus 2. Okay, but we have here from here we have that n plus 2 is equal to root over 1 plus n plus 1 into n plus 3. So I have this fn is equal to n into n plus 2, and which is equal to n into this. Okay, now we can also observe that this thing inside the root n plus 1 plus n plus 3 into n plus 3 can be represented like this, which ultimately is fn plus 1. So we get this equation 1, that is fn equals n into n plus 2, which is equal to n into root over 1 plus fn plus 1. Okay, so I put the value for n equal to 1, we have f1 equals 3. You can easily evaluate that, and then we proceed like using this equation 1. So 3 would be equal to 1 into root over 1 plus f2, which is equal to, we will put the value of f2 here, that is 2 into root over 1 plus f3. We will put the value of f3 here, that is equal to 3 into 1 plus f4, and so on. Going like this, we get equation 1. What is equation 1? This equation that Ramanujan got. Okay, so we got that. Now we get equation 1. See, so now uh, 4 can be written as this equation, this inequality 4, this inequality 4 can be written as this. Okay, how? See, from equation 4 we have r square. Now we take r inside the root. So when we take r inside the root, we get we are left with r square here, r square to the power 2, and so on. When it increases, we get r square to the power 2 to the power 2 to the power 2 n minus 1 times. So that is r to the power 2 to the power 2 n minus 1 n times. Okay, into, here I put the value 1 plus n plus 1 n plus 3. How? See this, f, I put fn here. Okay, I am putting fn here. Okay, see, and here see, look closely here. I have written 2n minus 1, which represents this function. I have defined this function 2n, which is equal to 2 to the power 2 n minus 1 times n times. Okay, so here it will be 2 to the power 2 n minus 1 times, and which will be given which will be equal to r to the power 2 to the power 2 to the power 2 n times. Okay, now but we have from here, see, r is between 0 and 1, right? I have shown here, see here, r is between 0 and 1. So if some number is between 0 and 1, okay, then the exponential power of that number, if I put something in some integer in the power of that number, then that will be less than 1. That is pretty clear, isn't it? So r to the power 2 to the power I for any I belonging to natural number is less than 1. So there exists an n minus 1 belonging to natural numbers, such that for all n greater than n minus 1, we have 1 greater than this thing. Why is this so? Because this number will be some finite number. Okay, but when n tends to infinity, this number will tend to 0. This number will tend to 0. So we get this thing, isn't it? We get this thing, that is this sequence converges to 0 as n tends to infinity. And if this happens, then we will get some n1 such that this number is less than 1 for all n greater than n1. So we can select n epsilon equals n1, for which 4 is true. What is 4? See, this is true, and we needed to prove this, which if we prove this, then we have done this. So this is proved. Hence un converges to 3 exactly. Hence we prove that 3 un is converging to 3 exactly. So going backwards will be sufficient. We need to do some real analysis. If you want the PDF, then you can text me. Thank you.